This video was supposed to come out exactly 4 days ago, but I had a lot of plans, so I couldn't make it. When we're programming, we usually have no idea what's happening inside of our computers. We just write in our code and expect it to work. But when we input our code, our computer cannot understand this code directly. So in order to run this program, it must be translated so the computer can understand. First, the code is passed through the compiler. This converts our high-level code into a more lower-level code. This is typically as assembly, which our computer can now read. This then passes through the assembler, which converts our low-level code into machine code, which is ones and zeros. At this point, the program becomes an executable, and now the processor can actually follow. So let's say we want to add 5 plus 5. As high-level code, it would be written as x equals 5 plus 5. When we compile this down to some lower-level code, it would be written like this. When the program reaches the processor, the instructions aren't executed all at once. They're handled one at a time, like a repeating cycle. First, the processor fetches an instruction from the memory. Then it decodes what the instruction is asking for, in which case this is immediate 5, and which register it uses, which is register 0. Finally, it executes the instruction. This cycle will repeat for every single line, fetching our instruction memory, decoding the memory, and then executing the instruction. This is also known as the fetch, decode, and execute cycle. What the processor does during each of these steps is actually determined by the ISA, or instruction set architecture. The sequence determines how what we input will interact with the computer. With our line of code, we know we at least need 3 registers, at least 1 register for an immediate value, and something to add the value. This is our basic concept of hardware system architecture. Think of it like this: ISA is our language, English, and HSA is the speaker's voice, which can be different accents, different speeds, but still going to be the same words. The ISA defines what the processor must do, and the HSA defines how the processor actually does it. Let's take a dive into history a bit. This is the analytical engine. In the 19th century, Charles Babbage designed a mechanical general-purpose computer. This machine is considered a precursor to modern computers, introducing ideas like programming via punch cards, memory for storing data, and the processing unit known as the mill. Its general purpose is to perform any mathematical calculation it was given by the programmable punch cards. So where are these calculations actually done? The mill in the analytic engine is directly analogous to the arithmetic logic unit, or ALU, in a modern computer. The ALU is capable of performing operations like adding, subtracting, and performing bitwise operations. So how would we do something that can perform all of these operations? Well, let's go and start off by making a basic adder. But before I do that, allow me to jog your memory on the numerical system of binary. In Boolean, we use the values off and on, or 1 and 0. In this binary system, if we reach 1, we have to carry over to the left. Due to there only being 2 digits in binary, each place is worth 2 times more than the last. So how would I find the value in front of me? So first, we'd have to get 4, then 2, then 1. Then all we have to do after that is add them all together. And this brings me to the number 7. This is a truth table for a half adder. If A is 1 and B is 0, then the sum equals to 1. If A is 0 and B is 1, then the sum equals 1. But if A and B equals to 1, then the sum must be 0 and the carry must turn into a 1. So how would I add these two sets of data together? We know that if A and B is equal to 1, then the sum must be 0 and we must carry over the 1. This goes on for the rest. So how would we make this in-game? We know that if both A and B is on, then the sum will be 0. So we can use an exclusive OR gate for that, because if both inputs are on, then it will turn off. Now if both inputs are on, then it has to carry over to the other side. We can use an AND gate for that. So if one input is on, then the sum is 1, but if both are on, then the 1 carries over. It works, but if you take a look back at our equation, we would have to take in a carry input. So let's add in another input and also modify this a bit. So if A is on, then the sum is 1, but if B is on, then it carries over. Now if you take in a carry input, then the sum is 1 and the carry is 1. Now that we have our full adder, let's go and make a basic 4-bit adder. I'm going to compress this down and then make some inputs for us. A carry input and 2 4-bit inputs. I'm going to start off by plugging in my carry input into my carry in. Now let's just plug in our carry outputs into the other carry inputs. Next I'm going to plug in my sums into my outputs. then my final carry output into the carry output. Now it is time to just plug in our 4-bit inputs. This brings us to this. Ignore what I have on the right. This is a pre-made display I made. But let's try 1 plus 1. And that gives us 2. Now let's go and try 8 plus 4. And it gives us 12. So this is just adding. How would we get subtraction? Well, this is when I bring in the signed negator. Well, it's not that advanced or anything. Basically, the last is negative. So how would the signed negator look like? So first, it would go up normally. But once we reach the last bit, then it would turn into a negative, as -8. Now then, it will count back down from -8 down to -1. Then after -1, we reach 0. So with that knowledge, how would we use the sign negator to make subtraction? Well, that's pretty easy. All we have to do is just use an exclusive OR gate on the second bin of inputs. We can use our carry-in to toggle our sign negator. There is a slight problem when building this though. All of them on would be considered -1. We want it to start at 0. Now let's take in our carry-in and bring it over to the carry input. I'm going to add in some extra pins like the toggle output and the toggle for the subtraction. Later on, I'll explain why we need this, but for now, let's just stick with this. To make sure our toggle output works, let's press in some random numbers. Now, if it's on, then it should now output stuff. Alright, let's do normal math. Let's say 4 plus 2. That equals 6. Now let's try -4 plus 2. And that equals -2. So we have now gotten our first 2 operators, add and subtract. So how do we add in our other operators like AND, OR, and exclusive OR? Well, we can just plug them in directly, but there will be some issues with that. How do we choose between which operator should be used? Well, this is where the decoder comes in. If you haven't watched the past video where I explain multiplexers and decoders, then I please do recommend going back and watching it. So to start, I'm going to give some individual pins for our inputs. Just imagine that the OR gates are our input pins. It's just here to make my life a little bit easier when it comes to building. For short, we're going to need to sort of multiplex our data so we can select between what operation should be used. To help you understand, I'm just going to go straight into building the operators. I'm going to connect this to an AND gate to once again make this a toggle. Now let's individually plug in our input pins into our inputs. Now that I have that done, I'm going to make the first column the AND gate, the second column the OR gate, the third column the NOT gate, and the last column the NAND gate. So directly plugging in the Bitwise operator's outputs into the ALU's output, you can already see there's some interfering issues with this, and this is where the decoder comes in. So let's go and take a look at our instructions right here. So if all selector pins are off, then the AND operator should be sent out. If the value is 001 on the selector pins, then the OR gate should be sent out. I'm going to do this for the rest of the Bitwise operators. And we can now select between which Bitwise operator should be used. If you're wondering why I didn't add exclusive OR gate on there, it's because I can make that using memory, but we're not on that subject yet. And those 2 spaces will be reserved for division and multiplication, which will be explained once I have RAM. So 110 means that it should add. So let's just go plug this in into our toggle switch or our adder. I'm also going to test if it works. Now time for subtraction. If all are on, then the toggle for the adder and the subtract signal should be on. Now that we have completed the ALU, let's go and test if this works. Currently, the selector pins are on the AND gate. The AND gate only sends an output of high if 2 of the same inputs are on. And now for OR, it's either OR, input A or input B. For NOT and NAND, it's just the inversion of and OR. And the selector pins for add, 4 plus, say 2, and this brings us to 6. Now let's go and test for subtraction. 2 minus 8, and that gives us -6. So now you know how your computer can do basic mathematical operations, like adding and subtracting, or doing bitwise operations with the given instructions. In the next video, I will be explaining how computers can remember data and store data. If you guys have any questions or have any suggestions for the next video that should be explained, then please comment it down below. But that is all for today. See y'all and bye.